So now let's talk about chemical equilibrium. So let's first consider a standard reaction schema like this. BB plus CC equals to DD plus EE. I'm going to reserve A for activity. And this represents a reaction's reactants. And this represents its product. So let's just perhaps take into account a very simple reaction, Al2O3 plus 3H2, 2Al plus 3H2O. This over here you can assume is 1. This term is lowercase b. This term is b. This is c. This uppercase c. This is lowercase d. This is uppercase d. This is lowercase e. And uppercase e. So that's what it really means. If we were to take the equation for reversible work, delta G is equals to delta G plus RT ln J. J is essentially this with the different coefficients substituted in. At equilibrium, this J is also known as the equilibrium constant. Also at equilibrium, we know that this delta G is equals to 0, and we can rewrite that expression as this. So this is called the standard Gibbs free energy of the reaction, and it's given in the unit joules. So let's consider the example of copper oxidizing. We know that copper, in the presence of oxygen, will eventually oxidize to form these products. And if we were to oxidize it furthermore, it will end up with even more products such as the CuO wire. Here, I want to focus primarily only on this process, which is expressed in this reaction over here. So, if we were to substitute this directly into the equation for standard Gibbs free energy, you will notice that the values here have been substituted here, and the values have been substituted here. Now, remember, we assume an ideal gas condition. In the ideal gas condition, we can assume that the ambient pressure is equivalent to the pressure of oxygen. So, the term PO2, which we're solving for, is called the equilibrium O2 pressure, which is essentially the pressure where no reactions take place. So let's try and understand that with a simple problem. Here, at 1000 Kelvin, we want to find out what is the pressure of O2 such that the reaction is in equilibrium. So what I really want you to do is to figure out what is PO2. Now, if pressure is higher than PO2, then oxidation will take place. But if pressure is lower than PO2, reduction will take place. At PO2, there will be no reaction. The good news is that chemical handbooks usually give you the G naught of many different kinds of metals, and all you have to do is substitute in directly. From then on, all we have to do is to substitute 1000 K for us to get this expression over here, where this is the gas constant, this is the temperature, and we need to solve for PO2. Remember, this came from this expression, G naught equals to negative RT ln K. So, from here, if we do it right, PO2 works out to 1.14 times 10 to the power of negative 10 atmospheres. Notice that this is actually a very low pressure to overcome. In most circumstances, especially in 1 atmosphere, copper will definitely oxidize. Oxidation of copper depends on the pressure of O2. When the pressure is above the equilibrium pressure, the activity of copper will be less than 1 and will oxidize to be copper oxide. Similarly, when O2 is below the equilibrium partial pressure, copper will be stable, or copper oxide might even be reduced back to copper. At equilibrium, copper will exist with copper oxide. This graph is a plot of the standard Gibbs free energy of reaction versus temperature, which allows people like metallurgists to determine the desired O2 pressure for any kind of process that they want. So remember that T can change. To maintain equilibrium, P must change and so must delta G naught. So here, this line represents the equilibrium condition for copper and copper oxide. Anything above this line, copper oxide is stable and will form. Anything below this line, copper is stable and there will be no oxidation.